Hi girls, I'm just going to record you a video that takes you through your titration study questions, just so that you can use it as you need, just fast forwarding to the questions that you need and so on. So I'm going to start with the multiple choice questions and have a look at this first question, which a lot of people got wrong. So just be really careful with a question like this, where you're asked for the concentration or number of moles of ions in a solution. So it says how many moles of hydrogen ions are present in 40 centimetres cubed of 0.2 molar sulfuric acid. What you need to think here is the formula of sulfuric acid is H2SO4. So you need to write an equation for the dissociation of sulfuric acid in solution. It's going to produce hydrogen ions, H+, and sulfate ions, SO4 2-, but then you need to balance that. And you can see, because the formula of sulfuric acid is H2SO4, that you need to put a 2 in front of your H+ ions. So then from that point you can calculate your number of moles, N equals CV. So it's concentration 0.2 times by 0.04, converting that 40 centimetres cubed into decimeters cubed. That comes out as 8 times 10 to the minus 3 moles. And then bringing that across to your hydrogen ions, that's a 1:2 ratio. So you're going to get twice as many moles of hydrogen ions, which is 0.016 moles, or as the answer puts it, 1.6 times 10 to the minus 2. So just be careful with those questions. Writing your dissociation equation to see how many, what your ratio is of your salt or your solution to the ions that are formed from it. Then having a look at number 2. Again, a diagram might help with this. I know that it's just a 1-mark question, but a diagram could help. So essentially what you're starting with is a 4.64 gram sample of your hydrated sodium carbonate. And so that is your original sample. That is all transferred into a volumetric flask. That is 1 decimeter in volume. Not often we get a volume of 1 decimeter cubed. It's normally 250 or sometimes 500, but that's made up to 1 decimeter cubed. So that is then going to be your sodium carbonate solution. And remember that when that's dissolved in water, it reacts essentially as the anhydrous salt. Okay, and so that's 1 decimeter cubed, and that's your volumetric flask. Okay, then we are taking 25 centimeters cubed of this solution and putting that in a conical flask for titration. So I'll draw your conical flask. Again, the diagram's not perfect, but let's think about 25 centimeters cubed. What fraction of that is or in our conical flask? So 25 out of 1 decimeter cubed is 1/40th of your sodium carbonate solution. And that is 25 centimeters cubed overall, and that's in your conical flask. Okay, and then that is goes in your titration. So if you draw your burette there, we're titrating it against hydrochloric acid, and there's your concentration, 0.05 molar, and your average titer is 20.0 centimeters cubed, which is 0.02 decimeters cubed. So in order to do this calculation, we need to think of our balanced symbol equation for this reaction. So we've got sodium carbonate reacting with hydrochloric acid. That will produce the salt sodium chloride plus water plus carbon dioxide. To balance that equation, you can see that you need 2 sodiums on the right hand side. Then you need 2 chlorines on the left hand side, and that then balances your hydrogens as well. So what you're thinking here is about your ratio. So we're starting with our number of moles in our burette of hydrochloric acid. We'll be bringing that over to sodium carbonate to get the number of moles there. You can see your ratio is 2:1, moving from your hydrochloric acid to sodium carbonate. So that means once we've got our number of moles of hydrochloric acid, we need to half them to get the number of moles of our sodium carbonate in the conical flask. So we're dividing by 2, and that's because our ratio is 2:1. Okay, then how many moles of our sodium carbonate would we have had in the volumetric flask? That's going to be times by 40, because we only have 1 out of 40 of our portion of sodium carbonate in here. And since all of our original sample was transferred into that solution, that means the number of moles that we get in the volumetric flask is the same as the number of moles in the original sample. So yes, a lot of working out there, but if that helps you make sense of the question and get the right answer, then that's worthwhile. So as always, we start our equation, our calculation, with the number of moles of hydrochloric acid from our titration. So that's going to be our concentration of 0.05 times by our volume of 0.02. And that gives us 1 times 10 to the minus 3 moles. Then we are essentially dividing that by 2, just as our ratio is here, because our ratio is 2 to 1, so dividing by 2, timesing by 1. That means we've got 5 times 10 to the minus 4 moles in our 25 centimetre cube sample in the conical flask. We then need to work out how many moles do I have in my volumetric flask. And so to do that, tracking back in your diagram, we times by 40. And so that gives us 0.02 moles in 1 decimetre cubed. Okay, and then that's essentially times by 1 to give us 0.02 moles of sodium carbonate in your original sample. Okay, so we want to essentially work out the number of water of crystallization. We now know that 0.02 moles of sodium carbonate makes up our hydrated salt. So we want to work out the mass of that, so we can then work out the mass of water in our hydrated sample. So the mass of Na2CO3, which is essentially your anhydrous, is going to be your 0.02 moles of your sodium carbonate times by the RFM, which is 106, and that comes out as 2.12 grams of sodium carbonate in your original sample, and that's essentially your anhydrous mass. We then need to work out the mass of water, and we do that by taking our hydrated and taking away the mass of the anhydrous. So the hydrated salt is our original sample, which, look back at the question, was 4.64 grams. We're taking away our 2.12 grams that we've worked out from our titration, and that should come out as 2.52 grams. We now need to work out our number of moles of water to get our ratio. So we put our anhydrous sodium carbonate to our water. We actually already know our number of moles of sodium carbonate. We worked it out up there was 0.02, or again you can do 2.12 divided by your RFM, and that's going to be in a ratio of your water, which is 2.52 divided by the RFM of water, which is 18, and that comes out as 0.14. Divide by your smallest number of moles, which is 0.02, and that goes to a ratio of 1 to 7. And so going right back to your question, your answer is C. Question 3, we were asked to work out the concentration of our solution of sodium carbonate. So remember, concentration is the number of moles in a given volume. So you can see all the units here are moles per decimetre cubed. So what we need to work out first of all is our number of moles of sodium carbonate by doing N equals mass over RFM. So that's 2.65 divided by our RFM, which is 106. That comes out as 0.025 moles. And then simply using your C equals N over V, which is 0.025 moles, divided by your volume, which is 250 centimetres cubed, that would be 0.25 decimetres cubed. And that comes out as 0.1 moles per decimetre cubed. So your answer is C. Question number 4 then. You need to think in this question about your ratio of potassium hydroxide to sulfuric acid. So a lot of people choosing the wrong answer with this one as well. So potassium hydroxide is KOH plus your sulfuric acid, H2SO4, giving you K2SO4 plus H2O. That's not balanced though. We need 2 in front of our KOH and we need 2 waters. So we can work out how many moles of sulfuric acid we have and therefore how many moles of potassium hydroxide we're going to need. So we have 50 centimetres cubed of 0.2 moles per decimetre cubed sulfuric acid. So we can work out N equals CV, that's 0.2 times by 0.05, which gives you 0.01 moles. Bringing that over to your potassium hydroxide, the ratio of sulfuric acid to potassium hydroxide is 1 to 2. So we're timesing by 2. So that means I actually need 0.02 moles of potassium hydroxide. So a lot of people just went down that list and worked out how many moles there were as the same as sulfuric acid. But we actually need twice as many moles of potassium hydroxide. So at this point you can do one of the 2 things. You can work your way through down through the options and do N equals CV for all of them. And what you'll find is that it takes to part D to get that answer. So N equals CV there will be 0.02. Your other option is to think of this equation, N equals CV. And if I want twice as many moles, so if I want N to be twice as many, then if I'm keeping the concentration the same, so if that's times by 1, then the volume I will need to double. Or if I am... let me write that out again. If I want twice as many moles and I'm keeping the volume the same, then I will need twice the concentration. So we'll try that blue one first because that's the first option. We've got twice the concentration, but we would need the volume to stay the same. But the volume has doubled as well. So actually we would end up with 0.04 moles of potassium hydroxide here, which is obviously not the answer. So then we look through these options of where we're keeping the concentration the same. I'll underline those in red. That's up to this option here. And we're looking for where the volume has doubled. And the volume has doubled in part D, which is our answer. Question number 5 then. This was just almost like a reacting amounts calculation. So you had to write a balance symbol equation first of all. And that's really important because it gives us our correct ratio. And they will throw in an answer there that will be the correct one if you didn't balance your equation. So be careful about that. So calcium carbonate plus hydrochloric acid gives calcium chloride plus water plus carbon dioxide, and you need 2 HCl here. So we're looking for the mass of calcium carbonate, so that's our question mark, which will exactly neutralise 500 centimetres cubed of 0.1 molar hydrochloric acid. So N equals CV with our hydrochloric acid, 0.1 times 0.5, which is 0.05 moles. What is our ratio? It's 2 to 1. So we divide by 2 and that gets us 0.025 moles of our calcium carbonate. And then we do mass equals N times RFM. That's 0.025 times by your RFM of calcium carbonate, which is 100. And so that's going to give you 2.5 grams, which is answer B. Question number 6 asks us to calculate the molarity of this solution of chlorine water. And it says that it dissolves to the extent of 0.8 grams in 100 centimetres cubed. So molarity really means the concentration in moles per decimetre cubed. A lot of people just calculating the number of moles. That's not what molarity means. The molarity means the concentration in moles per decimetre cubed. But you must use the units of capital M, and we often use that with our titration calculations when we're talking about concentration. We talk about 0.1 molar hydrochloric acid, and that's what the molarity is, but it's equivalent to the concentration in moles per decimetre cubed. So what that means is it allows us to calculate the concentration using C equals N over V. But because we've been given a mass, we need to calculate the number of moles first of all. So we do N equals mass over RFM. Be careful, chlorine is Cl2, you're even given that in the question. So it's 0.8 grams divided by 71, 2 times 35.5. And that comes out as quite a long answer of 0.0112676, and probably continuing on, moles. And then we use C equals N over V. So that's going to be our 0.01126, etc., divided by 0.1. Keep that accurate in your calculator until the final answer, and that will come out as 0.1126, etc. And you could round that off to 0.113. But the units you need to use are capital M because it asks for the molarity. So some people lost a mark because they wrote moles per decimeter cubed. Question number 7 is about a titration that involves determining the degree of hydration. It asks you, first of all, what is a standard solution? And that's a definition that you should definitely know. And it's a solution of known concentration. Okay. Give the equation for the reaction between sodium carbonate and hydrochloric acid. That's Na2CO3 plus 2HCl, giving you NaCl, and you'll need 2 of those, plus H2O plus CO2. This is a really common example with the degree of hydration calculations, and so make sure you know that equation well. Know that a metal carbonate reacts with acid to produce a salt, water and carbon dioxide, and then balance from there. Name a suitable indicator for this titration. This actually needs to be methyl orange. Sodium carbonate is technically not a base because a base is something that reacts with an acid to produce a salt and water only. You can see that we're also producing carbon dioxide gas, which is an acidic gas. So this is not a neutralization reaction as such. And so we don't technically call sodium carbonate a base. But in terms of determining your indicator, we treat it as a strong acid versus weak base type titration. And so that means we need to use methyl orange and not phenolphthalein. So the indicator will be methyl orange. Then we're given some of the experimental information. We're told that we start with 3.57 grams of sodium carbonate, and it will be hydrated sodium carbonate because we're told in the question that's what we're trying to determine, the number of moles of, the degree of hydration. And it says here it was made up to a 250 centimetre cube solution, and then we titrate 25 of that against our 28.5 centimetres cubed of 0.1 molar hydrochloric acid. And again, you could draw out a diagram for this reaction, which I'll do in just a second. It says here to give the colour change, which would be obtained at the end point using your indicator named above. So that's your methyl orange. So what you're thinking is that it's always from the conical flask, whatever solution's in your conical flask, to whatever solution is in your burette. So in this case, we're going from base, or sodium carbonate. It's technically not a base, but essentially a base, to what's in your burette, which is an acid. So therefore we're going from yellow to red with our methyl orange. So down at the bottom, I'm going to do a diagram for this experiment. And if you are finding you're making mistakes in these calculations, I would give the diagrams a go and see if they help you. Because even if you lose 1 or 2 marks along the way, that all obviously adds up. So you're starting with your hydrated salt, 3.57 grams of that. And so we could say this is Na2CO3.XH2O. If you look towards the end of the question, that's what we're going to be asked to work out. So that's essentially your original sample. So we want to essentially work out how many moles of sodium carbonate do we have in this original sample. And that gets us the number of moles of our anhydrous salt, and we can work out the mass of the anhydrous salt and then the mass of the water. So it says that's made up to, will be all transferred into a volumetric flask and made up to 250 centimetres cubed. Okay, so that's going to be then our sodium carbonate solution. Remember, once that is dissolved, then it breaks away. The water of crystallization breaks away and mixes in with the other water molecules that you're dissolving it in. So it reacts then as the anhydrous salt. So that's the volumetric flask. We're then told that a 25 centimetre cube sample is taken out for titration ultimately. So that's going to be 25 out of our 250. So what portion is that? That's a tenth. That's a tenth of our sodium carbonate solution. That is 25 centimetres cubed. Sorry, this is very messy. And that is our conical flask. So in case they ask us how many moles of sodium carbonate is there in the conical flask, we're then going to take that and do our titration from that. Okay, and that is being titrated against, in the question, as you're told, 28.5. That's your average titer. Your concentration is 0.1 molar HCl. And your average titer is 0.0285 decimeters cubed. So earlier on in the question, if you look up at 7a, part 2, we were asked to write a balanced symbol equation for this reaction. And we found out that's Na2CO3 plus 2HCl. The rest of it doesn't matter at this point, but we need the whole equation to get our balancing number ratio. So we're going to work out the number of moles of hydrochloric acid up here, and we want to bring that over to the number of moles of sodium carbonate. That's a 2-to-1 ratio, so we're dividing by 2. So tracking back our moles, once we've got our number of moles of hydrochloric acid from our titration, we divide by 2 to get our number of moles of sodium carbonate in the conical flask. That was only 1/10 of the portion, so we times by 10 to get how many moles there are in the volumetric flask, and how many moles of sodium carbonate then are there in the original sample. There is 1. So diagrams like that might help. So let's have a look at the parts of the question. And it says calculate the number of moles of hydrochloric acid used in the titration. Well, in terms of what stage we're at in our calculation, that's right at the start, looking at our titration. So we're looking at how many moles do we add from our burette. So we're simply doing N equals CV, which is going to equal 0.1 times by 0.0285, which it gives us 2.85 times 10 to the minus 3 moles. Then it says calculate the number of moles of sodium carbonate present in the 25 centimetre cubed of solution. Think about what piece of apparatus you're in. You're in the conical flask at this stage. So that's where we use our ratio. Look down at your diagram to help you with that. And we're essentially going to this stage now. How many moles are there in the conical flask? Well, we said we just take our number of moles from the first part from our titration and we divide by 2. So you're simply dividing by 2 because of your ratio, and that will give us 1.425 times 10 to the minus 3 moles of sodium carbonate in our conical flask. Going over to the next page, but I've brought my diagram with me. It says calculate the number of moles present in the 250 centimetres cubed of solution. That's us going back to the volumetric flask. So essentially here we're timesing by 10 because in our titration we only had 25 out of 250. In other words, 1/10 of the moles in our conical flask versus our volumetric flask. Remember, we're working backwards to get the number of moles in the original sample. So times your value from part 3 by 10, and you're going to get 0.01425 moles present in your 250 centimetres cubed of solution. Calculate the mass of sodium carbonate present. Well, if we look back, we can see that to get our number of moles in our original sample, we just times by 1. So it's going to be the same number of moles, 0.01425. Mass equals N times RFM. That's going to be our 0.01425 times by 106, the RFM of sodium carbonate, and that works out as 1.5105 grams. And at this stage, because our mass in the original sample was given to us to 2 decimal places, we could round that off to 1.51 grams. Calculate the mass of water present in the second sample. That's going to be your hydrated minus your anhydrous. So that's 3.57 minus 1.51 that we've just worked out from our titration. And that gives us 2.06 grams. Just make sure you include your units as well. Some people dropping off units, but mass should be in grams here. Then calculate the number of moles of water present in the second sample. So we're kind of done with our diagram. We can get rid of that. Number of moles of water present is going to be N equals mass over RFM, which is the 2.06 grams of water divided by 18, which would give us 0.1144. And finally, calculate the value of X in the second sample. You're doing your ratio of the moles of sodium carbonate to water. So that is 0.01425 to 0.1144. You divide by your smallest number of moles, which is this one of sodium carbonate. So divide by this, and that gets you a ratio of 1 to 8. And so therefore X is equal to 8. Question 8 then is a dilution question, so it's of the analysis of vinegar, and you can see from the question that we are taking 25 centimetres cubed of undiluted vinegar and diluting that up to 250 centimetres cubed. So even at this point, even if the question doesn't necessarily lead you this way, sometimes it leads you to track the number of moles, but in this question, if we calculate the dilution factor from the start, remember it's the new total volume, which is 250 centimetres cubed, divided by the initial volume, or the volume of your original sample, which is 25. So that's times by 10. And you'll see at the end of the calculation that that is the way this one leads us. So that's worthwhile calculating at the end. So this is essentially vinegar, which is ethanoic acid, titrated against 0.1 molar sodium hydroxide until your endpoint is reached. So it doesn't ask you until the following page, but you can see here in the following page it will ask you to fill in the results table with your titers, so your 2 accurate titers. So we could do that at this point just while we are on the table. The titer for the first accurate ends up being 21.4 and of the second accurate being 21.3. We're first of all asked to name an indicator for this titration, and this is a weak acid versus a strong base, and so therefore we must use phenolphthalein in this titration. Try and get your spelling of phenolphthalein right. If you haven't learned that yet, please do learn it at this stage. And then it asks us what colour change will be observed. Remember, that's always from conical flask to the burette. So in our conical flask, we're going to have our vinegar, which is an acid. So that is colourless in phenolphthalein. And then in our burette, we have alkali, and that is pink in phenolphthalein. Over on the next page, you're asked to write your equation for the reaction. This is essentially your titration equation, and you can see that's given there. Ethanoic acid plus sodium hydroxide giving you sodium ethanoate plus water, and that's already balanced. So complete the results table, which we've already done, and calculate the average titer. So your 2 accurates were 21.4 and 21.3. Divided by 2, that gives us 21.35 centimetres cubed. You must include a unit, otherwise we don't know what unit of volume that's in. Then it says use the average titer to calculate the number of moles of sodium hydroxide. We were told in the question that that was 0.1 molar. So we're just simply using N equals CV with 0.1 and 0.02135 from our average titer. Do not round that off. At this stage, some people are rounding that off to 21.4, which looks like you're just using your first accurate. So don't round that off at this stage. So that comes out as 2.135 times 10 to the minus 3 moles of sodium hydroxide. Then it says calculate the concentration of ethanoic acid in the diluted vinegar. Well, what we have to think first of all is how many moles of ethanoic acid are we going to have? Well, if you look up at your equation again, we're taking our number of moles of sodium hydroxide and bringing that over to ethanoic acid. That's in a 1-to-1 ratio. So the number of moles in our 25 centimetre cube sample is 2.135 times 10 to the minus 3 moles in our 25 centimetres cube sample because of our 1-to-1 ratio. And we're essentially working out what is the concentration in moles per decimetre cube. So you can either think of that as, well, if I've got that number of moles in 25 centimetres cubed, I would times that by 40 to get how many moles there are in 1 decimetre cubed, or literally just use your equation C equals N over V. Our number of moles in the conical flask is 2.135 times 10 to the minus 3 divided by our volume, which is 0.025, because that is the number of moles in our conical flask. Lots of people at this point dividing by 0.25 rather than 0.025. But think about what volume, that's our number of moles in 25 centimetres cubed. So that's why we do it divided by 0.025. That will then come out as 0.0854 moles per decimetre cubed. And then finally, calculate the concentration of the undiluted ethanoic acid in the undiluted vinegar. We're thinking back to the start of the question where we worked out our dilution factor was times by 10. So what we need to do is take our concentration of our diluted vinegar that we worked out in the previous part of the question and times that by 10. That would get us 0.854 moles per decimetre cubed. Part C then asks you to describe, giving practical details, how you would prepare the solution of diluted vinegar and then transfer to a conical flask. So 2 parts of this. How would you prepare the solution of diluted vinegar? So that's essentially making that up in the volumetric flask. And then secondly, transferring 25 centimetres to a conical flask. So here's the mark scheme answer, so you can have a look through this and see any of the points that you were missing and fill those in. So first of all, we need to think specific to this reaction, how are we preparing the solution of diluted vinegar? Remember, we were told in the question that we were taking 25 centimetres cubed of our original or undiluted vinegar and making that up to 250 centimetres cubed of your diluted. So how do we do that? Well, first of all, the mark in the mark scheme was for rinsing the pipette with undiluted vinegar. Anything you use a pipette for, you've got to rinse it. So you can see that's significant in this mark scheme. It's worth 2 of our overall marks. So remember, we're going to use a pipette to get accurately 25.0 centimetres cubed of our original solution, and we're going to then put that into a volumetric flask. So that essentially covers the first few points in the mark scheme. This one I have in brackets was not actually mentioned in the mark scheme, but you would need to state it to make your answer make sense if it's a proper method of how you prepare the solution. So rinsing the pipette with undiluted vinegar. Randomly they give a mark for the use of a pipette filler, so you might say attach a pipette filler to a pipette and rinse it with undiluted vinegar. Then you transfer 25.0 centimetres cubed of your undiluted vinegar into a 250 centimetre cube volumetric flask. It's important that you mention the volume of the volumetric flask because there's different sizes of volumetric flasks and you want to pick the volumetric flask that has the volume matching the volume of solution that you want to make up. And it says add deionized water until the bottom of the meniscus is on the 250 centimetre cubed mark. This is really important. Bottom of the meniscus is on the mark. You can't just say meniscus because the meniscus is a curve. And so therefore, if the top of your meniscus is hitting the mark, then that's not actually the accurate volume. So that's not right. We want the bottom of the meniscus on the mark. Okay, so you've got to be specific about that. Then it talks about mixing or inverting the solution, the volumetric flask. Talk about putting your stopper in first, otherwise your solution's going to go all over the place. Then what we want to do is talk about the second part transferring the solution, 25 centimetres cubed of it to a conical flask. Again, you're using a pipette, so you need to rinse the pipette with the diluted vinegar this time. Some people just saying rinse the pipette with vinegar, but you need to specify, is that the undiluted or is that the diluted? But of course, we're using the diluted vinegar in our titration, and so therefore we rinse it with the diluted vinegar and then use the pipette to transfer 25 or 25.0 centimetres cubed into the conical flask. Although again, that's in brackets because it wasn't mentioned in the mark scheme, but it would be needed for a full answer. In other words, really for your quality of written communication and for your answer to make sense and fully talk about the method. So go back to your notes and read over that method again. That is something you could be asked to describe, so make sure you know that method of dilution really, really well. Okay, number 9, water crystallization calculation again. So what is meant by the term standard solution? Again, that's a solution of known concentration Our next question is a balanced symbol equation that we've met a couple of times already in these questions. So you can see how common it is for that to come up. So make sure that you know that equation well. So again, this is really similar to the one that we were doing just a couple of questions previously. So same method, but this time just different values. We're starting with a 2.8 gram sample of our hydrated salt of washing soda crystals. That's being made up to 250 centimetres cubed. Then 25 centimetres cubed of that is being titrated against 22.4 centimetres cubed. That's our average titer of 0.1 molar hydrochloric acid. So again, you could do a diagram. Let me do a quick one down at the bottom here. Might not draw my apparatus this time, but even if you think about tracking your value, so 2.80 grams of your original sample, that's going to be your Na2CO3.xH2O, your original sample. That's then all transferred into a 250 centimetre cubed volumetric flask, and we get 250 centimetres cubed of our sodium carbonate solution. And that's in our volumetric flask, so you don't even need to draw out the apparatus if you don't want to. And then 25 centimetres cubed of that is taken, and so then we end up with a tenth of our sodium carbonate solution, and that's in our conical flask, and then we titrate that. So that's then going to go to our titration against your hydrochloric acid, which we're told has a concentration of 0.1 molar, and the volume, the average titer, is 0.0224 decimeters cubed. Again, let's think of our balanced symbol equation. The start of it is Na2CO3 plus 2 HCl. That's really all that we need here. So once we've got our number of moles of HCl, we're going to need to divide that by 2 because our ratio is 2 to 1. So from our titration to our conical flask, we're dividing by 2 the number of moles. To go from our conical flask to our volumetric flask, we're timesing by 10. And to go from our volumetric flask to our original sample, that's the same way timesing by 1. So you can see these diagrams are ultimately the same each time. If it's a sodium carbonate against hydrochloric acid, your first sort of moles transfer will be divided by 2. Then if it's 25 out of 250, it's going to be times by 10. So you can see the similarities in these, but obviously you've got to check the values for the question. So number of moles of hydrochloric acid, we're just using N equals CV. So that's 0.1 times by 0.0224. And that will give us 2.24 times 10 to the minus 3 moles of our hydrochloric acid. Moles of sodium carbonate in 25 centimetres cubed. That is your conical flask. And we said our ratio is 2 to 1 of hydrochloric acid to sodium carbonate. So we're dividing by 2 here, and that will give us 1.12 times 10 to the minus 3 moles. Go back to your diagram if you need to understand why we're doing that. So that's essentially the number of moles of sodium carbonate in our conical flask. Number of moles of sodium carbonate in the sample. So that's essentially in our original. And if you go back down to your diagram, let's see if I can see it here. We're essentially going from this point in our conical flask all the way back to our original sample. So you can see that involves a times by 10 and times by 1. And so therefore we're just timesing by 10 here to get the number of moles in our original sample. And that's really because we only titrated a tenth of the portion. So that will be 0.0112 moles in our original sample. Mass is N times RFM, which is 0.0112 times by 106. You'll know that RFM off by heart by this stage. And that comes out as 1.1872 grams. But because our original mass is given to us to 2 decimal places, that should be the mass of your sodium carbonate as well. Mass of water, that is essentially your hydrated or your original sample. minus the anhydrous, which is what we've just worked out. So that is, go back to your original question, or you can see from your diagram here, that we had 2.80 grams in our original sample, minus 1.19 in our of anhydrous, and that gives us 1.61 grams of water. Moles of water is mass over RFM, which is 1.61 over 18, and that gives us 0.0894 moles. And then finally, we're doing a mole ratio of sodium carbonate to water to get our value of X. And that is essentially our 0.0112 moles of sodium carbonate to 0.0894. So put those values in here. And then divide by your smallest number of moles, which is 0.0112. And that gives you a ratio of 1 to 8, and so the value of X is 8. So we've done loads of practice in this set of questions alone of water of crystallization calculations. So you should be really, really confident in those by now. So go back and try any of those examples where you lost marks. Over to question 10 now. This is another method question. Again, make sure you know these really well and think about us either doing these in class, you did a dilution in class yourselves, and I demonstrated this method of making up a solution from a solid. So this is very like making up a solution of a hydrated salt. This is not necessarily hydrated, but it's done in the same way. So essentially the principle behind this is you need to measure out the specific mass of the substance, transfer it to the size of volumetric flask of the volume of solution that you're trying to make up, adding water until the solution is on the bottom of the meniscus is on the mark, and then stop, ring and invert to mix. That's really the principle behind it. But what you need to do is get some details about washings and things like that. So if you are a visual learner, you may find a diagram helpful with this. So think about what you're doing. You are, first of all, measuring out a mass of 5.2 grams. Then what you want to do is get that all to dissolve. So you put it in a beaker, and you put your solid in here, and you add a small volume of water. So usually about 100 centimetres cubed, especially since this is a slightly bigger solution, it would be fine to add 100 centimetres cubed of deionized water. I'll just put DW there, okay? And that is your 5.2 grams. 5.20 grams. I'll come back to that in a wee second, why that's important that you include that zero. But essentially, what are you going to need to do to get that dissolve? You're going to need to stir it using a glass rod. Okay, and then what you want to do is transfer that into a volumetric flask, and we need to make up a solution that's 500 centimetres cubed, so we would use a 500 centimetres cubed volumetric flask. And we need to transfer all of this into a volumetric flask. And the easiest way to do that is through a filter funnel. Now you'll notice the mark scheme doesn't mention a filter funnel. Sorry, my diagrams are awful. But that's how we would generally transfer that in. So that all goes through the filter funnel. So essentially what we want to make sure, all of this makes its way into the volumetric flask and then is made up to a specific volume. So what we talk about during this method is dissolving your all of your solid and then transferring into the volumetric flask. We can't just put the solid into the volumetric flask. We need to make sure it's all dissolved first of all, because if we have a little bit sitting at the bottom of the volumetric flask, it's not dissolved, it's not part of the solution, and it will not be part of the reaction, so we can't be sure of its concentration essentially. And so essentially why I want to point this out is about the things that we need to rinse. So what you need to do is rinse your glass rod with deionized water as you remove it from the beaker, because it will contain some of your solution, which contains some of your mass of your original solid. You'll then need to rinse the beaker because it contains some of your solution, and you'll also need to rinse the filter funnel if you are mentioning that. So that's what we need to rinse, and then we need to make sure all of those rinsings go into the volumetric flask. So it's no good just saying rinse the filter funnel in the beaker. You don't want to then rinse it and just chuck it down the sink. You want to actually make sure that goes all into the volumetric flask. So let's have a wee read of the mark scheme here. It says here, dissolve 5.20 grams of the solution. It's important that you include that second zero, because if you just wrote 5.2 grams, which a lot of you did, that could be, that's been rounded up from 2 decimal places to 1 decimal place. And that could be anything from 5.15, 5.16, 5.17. All of those would round up to 5.2. And then we've got 5.20, 5.21, 5.23 and 5.24. So all of those values round off to 5.2, but we want exactly 5.20 grams. So that's what we specify. So quote the exact value to the accuracy that it's given to you in the question. You would have lost a mark there if you wrote 5.2. So dissolve 5.20 grams of the solid in deionized water in a beaker. Don't do that in the volumetric flask. Then transfer the solution to a 500 centimetre cube volumetric flask. You need to state the volume because volumetric flasks come in different sizes. So you need to state that volume. Then we made up the solution in a beaker and stirred it with a glass rod. So we need to rinse those with deionized water and add the washings. That's just essentially the water that we've rinsed it with, which will contain some of the solution, to the volumetric flask. Then we make up to the mark by adding deionized water until, again here, the bottom of the meniscus is on the mark. We explained that earlier. It doesn't matter if the top of the meniscus is on the mark, it's still not enough. The bottom of the meniscus has to be on the mark. So don't just say until the meniscus is on the mark. That's not enough to say. And then finally, stopper and invert to mix. Do make sure you put the stopper in, otherwise you're going to be throwing your solution all over the place. So that is how you accurately make up a solution from a solid. And then finally, you have your calculation part of the question. So it says here, complete the table above. Now you need to be careful with this. You'll see some of you wrote 0 and I marked it wrong, and you'll be thinking, well, of course the difference between 19.3 and 19.3 is 0. But our burette readings are always to 1 decimal place, so you must write 0.0. Your titer is always final burette reading minus your initial burette reading. So therefore, if we want to work out our final burette reading, we need to do the titer plus the initial burette reading. So essentially with this one, we're adding these two values, 19.3 and 18.7, and that gives us 38 if you did that in your calculator. But remember, our burette reading will be to 1 decimal place, so it's 38.0. So if you just wrote 38, you can't get the marks. Titer is the difference between final burette reading and initial burette reading, so that is 18.9 for our second one. Calculate the mean or the average titer, and that is 18.7 plus 18.9 over 2, and that is 18.8, what unit? Centimetres cubed. You don't get the mark if you don't include your units. Okay, next question. Calculate the relative formula mass of the metal carbonate using the mean titer value. And here again, a diagram might be helpful to help you understand this question. But let me just try and talk you through it now. You can try your own diagram if that's helpful. You are also given the balance symbol equation for this reaction on the previous page. So use the information that you've been given. So we really only need the left-hand side of it. So I'm just going to write the left-hand side only. So that's X2CO3. I'll maybe move it up here just for a bit of room. X2CO3 plus 2HCl. Making sure you get that ratio right. So where do we start our calculation? Always with the number of moles of the thing in my burette, which is a hydrochloric acid. So that's N equals CV. Concentration being 0.2 from the question, and using our average titer. Some people went back to using one of their accurate values, but no, use your average titer, which will be 0.0188. So that will give us 3.76 times 10 to the minus 3 moles. That's in our titration. Okay, bringing that over to your X2CO3, your carbonate, the ratio is 2 to 1. So we're dividing by 2, and that gets us 1.88 times 10 to the minus 3 moles. Then we need to think about what that volume is in. So that is, or that number of moles is in, that is in 25 centimetres cubed in your conical flask. Okay, this is where a diagram might be helpful if you're not sure about this. What volume was our original solution? Our original solution was 500 centimetres cubed. So we need to work out the number of moles in 500 centimetres cubed. How do we scale that up from 25 to 500? Well, we times by 20. So we've taken a 20th of the portion out. And so therefore, that will give us 0.0376 moles in our 500 centimetres cubed sample, our whole solution. And that's the same as the number of moles because all of our 5.20 grams was transferred in. So that's the same as the number of moles in our original sample. Okay. And that's in your 5.20 grams original sample. What do we want to do at this point? Well, we want to answer the question which asks to calculate the relative formula mass of the metal carbonate. Let me move this over a wee second. And so that will be RFM equals mass over M. Our mass from the original question is 5.20 grams. We had 5.20 grams of our X2CO3. We now know the number of moles was 0.0376. So we put that into our calculator and we would get 138. So you can round that off to the nearest whole value, which is 138. Now, some of you went forward at that point and worked out what X was. That's not what they ask you to do. That's the next part. So if you find you've done the working out for the next part, then scribble that out of part 3 because your final answer for part 3 should have been 138, not 39 as it is in the next question. So identify a metal X. So X2CO3 is 138. So what we want to do first of all is take away CO3. So 2 X's is going to be 138 minus 1 carbon and minus 3 oxygens. And that works out as X2 being 78. So therefore 1X is going to be 78 divided by 2, which is 39. And that is the same as the relative atomic mass of potassium. So that's your final answer. So some people wrote that working out in part 3 and your final answer is 39 is part 3. So just be really careful. That should just be with part 4. So that's your titration study questions finished. If there's any questions that you still have, please just get in touch.